Discrete wavelet transform, DWT. Before discussing about discrete wavelet transform, first of all, it would be appropriate to discuss in general regarding Fourier transform, FT. Fourier transform, FT, was first invented by French mathematician and physicist Jean-Baptiste Joseph Fourier in 1822. Fourier stated that any periodical function can be represented as a sum of sine and cosine of different frequencies, each multiplied by a different coefficient. Fourier transform converts a signal from the time amplitude domain to the frequency amplitude domain. Images are considered as 2D discrete functions. To use Fourier transform to analyze images, discrete Fourier transform, DFT, is used. FT is a reversible transform, which means the original signal can be recovered through the inverse discrete Fourier transform, IDFT. However, FT has a drawback, i.e., it does not provide the information about the time at which the particular frequency exists in the signal. Fourier transform only captures the different frequencies in a signal and cannot detect when those frequencies occurred. To overcome this drawback, wavelet transform, WAIT, was introduced. Wavelet transform, WAIT, can be more useful than Fourier transform, since it is based on functions that are localized in both space and frequency/scale. Wavelet transform brings a multi-resolution framework. With this setting, the signal can be decomposed into components that collect the information at a specified scale, i.e., different frequencies are analyzed with different resolutions. The WAIT has numerous applications in remote sensing such as image registration, spatial and spectral fusion, feature extraction, speckle reduction, texture classification, and crop phonology detection. Wavelet transform can be broadly classified into two main groups, i.e., continuous wavelet transform, CWT, and discrete wavelet transform, DWT. Since DWT is continuous, as a result, there are an infinite number of scale and translation parameters which leads to an infinite number of possible wavelet functions. To overcome the shortcoming of CWT, DWT was introduced. In the DWT algorithm, an image can be analyzed by passing it through an analysis filter bank followed by decimation operation. The analysis filter bank consists of low-pass and high-pass filter at each decomposition stage. When a signal passes through these filters, it splits into two signals. The low-pass filter, which corresponds to an averaging operation, extracts the coarse, average, information of the signal. The high-pass filter, which corresponds to a differencing operation, extracts the detail information of the signal such as edges, points, and lines. The output of the filtering operation is then decimated by 2, i.e., a 2D transform is accomplished by performing two separate one-dimensional transform. First of all, the image is filtered along the row and decimated by 2, and it is then followed by filtering the subimage along the column and decimated by 2. This operation splits the image into 4 bands, namely one approximation band, which contains coarse information, and 3 detail bands, horizontal, vertical, and diagonal, respectively, which contain information about the salient features of the image such as edges, points, and lines. A J-level decomposition can be performed resulting in 3 J plus 1 different frequency bands. At each level of decomposition, the image is split into high and low frequency components. The low frequency components can be further decomposed until the desired resolution is reached. The pan-sharpening procedure for the pan-sharpening of panchromatic, PN, and multispectral, MS, images using DWT has been explained in section 3.1. Decomposition of an image using DWT.